So what we're going to look at is our basic refrigeration cycle today, and I'm going to go through it all pretty quick because we're making a video so you can stop and go back, check up on it. We're going to talk about all the components that make up the refrigeration cycle and what's going on inside of each component. So if you look at this, this is called a compressor. This is actually a scroll compressor by Copeland. It's one of the most common ones you're going to find in residential equipment. All right, a compressor is what we call the heart of the system because it pumps refrigerant throughout this system. All right, alone pumping refrigerant is basically just a circulating pump. All it's doing is removing refrigerant in the system. Now, eventually, we're going to hit this component over here that's called our metering device, and it's going to create a restriction. So when you have this pumping and you have a restriction, you end up with a pressure difference. So you end up with a high side and you end up with a low side. All right? When we come out of this compressor, this is called our discharge line. Our discharge line is hot, high pressure vapor. So our refrigerant is in all vapor form when it leaves here. We also say that it's superheated vapor because it's well above its saturation temperature. So our superheated hot, high pressure vapor comes out. This is on discharge line, high pressure. If you can get the camera in here, you can see it's going to run to these three small distributor tubes. All that's doing is putting that hot gas inside this condensing coil. As it circulates through there, we blow outside air across it. If I keep that refrigerant at, say, 110 degrees, and I'm blowing 95-degree air across it, I can remove heat from it. I can cool it off, right? Basic air conditioning principle is that heat moves from hot to cold. So if that 95-degree air is cooler than that 115, 120-degree refrigerant, then we're going to cool it off. Does that make sense? So we say we remove heat. Anytime we're cooling something off, we're removing heat. If we're heating something up, we're adding heat. So we cool it off, so we remove heat. We got a fan circulating that outside air. And what happens is, once that hot vapor gives off all of its heat to the outside air, it begins to condense. That's its dew point. All right, it becomes a liquid. Just like if you bring a cold cup of iced tea outside on a summer day, all the air that hits it turns into water. All the moisture in the air rather is going to turn into water and condense. It gives off its heat. It needs that heat energy to stay a vapor. Once I remove that heat energy, it can't stay a vapor anymore, and it turns into a liquid. That's going to be very important in our refrigeration cycle. So again, hot gas goes through here, it gets cooled off, and by the time it comes out, because it's going to come out through these tubes, it will come out as a liquid. So it will be 100% liquid, and that's we're going to call it subcooled, because we're going to be cooling it off past its saturation point. And saturation is the temperature at which it goes from a vapor to a liquid or a liquid to a vapor. We call that changing states. That's our saturation point. So it comes out as all vapor, it's superheated. It's above that point. Once we cool it off into a liquid and keep cooling it off, it comes out of what we call subcooled. So it's cooler than that temperature that it changed states. All right? You'll trace it out. It goes through a filter dryer, which dries any moisture that may have been in the system. There should be none, but if for any case there was, that would help dry it out, as well as any small debris. Again, good piping practices should keep that from happening, but if you have any small debris, that will catch it. But this liquid flows all the way until it hits that metering device. That particular metering device is called a TXV. With that compressor pumping, that TXV choking down that refrigerant, we're going to create a low pressure on this side of it. So that compressor is pushing to this point, increasing the pressure. Then it has to go through a tiny orifice, so it drops to a really, really low pressure. All right, once it does that, it becomes a cold refrigerant. Refrigerant is going to follow a temperature-pressure relationship. The hotter that refrigerant is, the higher pressure. The higher the pressure it is, the hotter it will be. So if I want to control that refrigerant's temperature, I have to control that refrigerant's pressure. That's what that compressor and this metering device do. So when I was on that high side and my pressure was high, I wanted that refrigerant hot because I wanted it hotter than the outside air because that's the only way I could get rid of the heat that's inside of it. But once I come here and hit this metering device, I'm going to go through my distributor tubes, and that refrigerant is going to circulate through all these tubes. All right, this is called my evaporator. This whole component is known as the evaporator. Metering device, distributor tubes, evaporator. The reason that's called an evaporator is once that liquid refrigerant hits that very low pressure, now it's allowed to flash off into a vapor. So my liquid refrigerant is turning into a vapor. In order for that liquid to turn into a vapor, it has to have energy. All right? It's going to use heat energy. Heat is a type of energy, and heat moves from hot to cold. 2 golden rules that will help us understand everything going on here. So as this turns from a liquid to a vapor, because I dropped the pressure, now it's free to vaporize, it's going to absorb a lot of heat. So where's it going to get its heat from? Well, it's going to get it from anywhere it can. First, it's going to pull the heat off all these copper pipes it's going through, right? But my airstream inside of my home is going to be blowing across that. So then it's going to start pulling all the heat out of the air that's in my house. That's how we go in at about 75 degrees. We blow across this cold coil. It's absorbing heat. We come out of my supply at about 55 degrees. If I'm going from 75 to 55, that's a 20-degree temperature difference. I call that, or we in the industry call that, our delta T. Right? That's how much did our temperature change from when our air went in until our air came out. Okay, so this evaporator coil is probably going to be operating ideally around 40 degrees. It can vary anywhere from 38. Some high efficiency equipment even operates close to 50 degrees. But we want this cold. We control how cold it is by controlling its pressure. Because again, refrigerant will follow a temperature-pressure relationship. If I control its pressure, I control its temperature. Outside, I got my pressure high on that condenser so I could get rid of heat. When I came inside, I dropped that pressure drastically so that I could absorb it. Now that refrigerant's colder than the outside air, or the air circulating through it, so now it's absorbing heat. If I have 75-degree air going across a 40-degree coil, now I have a temperature difference of 35 degrees, right? And heat moves hot to cold, so that heat's going to move from my 75-degree air into my 40-degree refrigerant. All right? So once I've absorbed all the heat that I can, again, I told you about my superheat, my subcool, and my saturation. The same thing is happening here. I've got that subcooled refrigerant that hits that metering device. Once it hits it, it instantly flashes off some, so I start out automatically at that saturation point. Remember, I said saturation is the actual temperature where it's going from a liquid to a vapor, or a vapor back to a liquid. All right? One cool thing about it is, no matter how much heat you add to it, as long as you've got liquid going to a vapor, you're not going to change the temperature in it. So you can keep adding heat, adding heat, adding heat. As long as that liquid is changing to a vapor, it's using all of that heat you're adding just to change states, and it's never changing its temperature. So if it starts off at 40 degrees right here, it's still going to be 40 degrees here, and it's still going to be 40 degrees here, until at some point I no longer have any liquid left to evaporate. Once that happens, I'm done saturating. All right, my saturation temperature is 40 degrees. I state that temperature all the way until all my liquid evaporated into a vapor. Now, if I keep adding heat to it, now that it's all vapor, now it's going to start warming up again. All right. Once it starts warming up, I call that superheat. Superheat is my temperature above saturation. Subcooling is my temperature below saturation. If I'm subcooled, I'm all liquid. If I'm superheated, I'm all vapor. Okay? So my idea is to turn all that liquid into a vapor by the time I leave this coil. I want to use as much of this coil as I can to turn liquid to a vapor, because that means I'm absorbing a lot of heat. But by the time I leave, I want to be all vapor. So if I have 12 degrees of superheat, I'm saturating at 40 degrees. That means I would be 52 degrees when I leave. All right. Something cool about this metering device is its job as a TXV thermostatic expansion valve is to maintain a certain superheat. So if I have a warm coil coming out, this bowl has refrigerant inside of it. If it starts warming up, it's going to expand. It's got to push this disc in, which will open up a needle in there and let more refrigerant in. The warmer this gets, the more refrigerant this thing's going to allow in there. And then if it gets so cool, that pressure is going to drop. It doesn't need as much refrigerant. That needle's going to close some more. As that needle closes, I've got less refrigerant going in there. So the job of this TXV is simply to maintain superheat. It's going to adjust how much refrigerant is allowed through this coil based off of the temperature of this copper pipe and my spring tension and the pressure. So it's doing a balancing act in there to keep it where it needs to be. All right. So once I finish going through here and evaporating, I come back to my compressor, and this is called the suction line. Suction line is cool, low pressure vapor. All right. This cool vapor is coming back on my suction line. It just goes right back to my compressor, and the cycle continues. All right. So just to recap our components, we have a compressor. I leave the compressor on my discharge line as a hot, high pressure vapor. I go into the condenser where I condense it into a liquid. So I leave as a warm, high pressure liquid. The pressure here and the pressure here is pretty much going to be the same. My discharge and my liquid line should have approximately the same pressure, within 1 or 2 psi's, hopefully. All right, so my high side pressure is all one pressure, but I went from a vapor to a warm, high pressure liquid. I hit a metering device, which restricts it. There, as soon as it comes out of that metering device, it starts turning into a cold or a cool or low pressure liquid that's vaporizing. All right, so I've got cool liquid flashing off into a gas as I go through here. When I leave on my suction line, I should be 100% vapor. A compressor cannot pump liquid. You'll damage your compressor if I send liquid back. That's why I need to make sure I have some superheat factors. I don't want too much superheat because that means, one, I'm not using my whole evaporator coil to absorb heat. And two, I'm going to have hot gas or warm gas coming to that compressor. Most compressors are cooled off by the refrigerant itself. So if it doesn't have cool vapor coming back to it, that compressor may overheat. So that's our basic refrigeration cycle. Compressor, discharge line, condenser. Liquid line, metering device. Evaporator, suction line, back to the compressor. And you think of it like a sponge. All right? We control the pressure, we control how much heat we absorb and how much heat we get rid of. If I have a bucket and I have a sponge and I don't want water in that bucket, I take that sponge, all right, as it's compressed, I stick it inside there. As I let go of it, it's going to absorb water, right? The same thing here. I have that compressed liquid. I release the pressure on it. As it expands, it absorbs heat, just like my sponge absorbs water. I then would take that sponge over here, and I would apply pressure. I would squeeze it. Once I squeeze it, what does all that water do? It falls out, right? So I'm doing the same thing with my refrigerant. I'm letting it absorb heat right here, and then as I go through the compressor, I'm compressing it down, and as I compress it down, it gets hotter, and basically I squeeze the heat out by blowing cooler outside air across it. And it's a repeating cycle, just like that sponge. I take the sponge back in there, I absorb more water, I dump it where I don't want it. Absorb water, dump it where I don't want it. Refrigerant's the same way. Absorb heat, dump it where you don't want it. Absorb more heat, dump it where you don't want it until that 80-degree house cools off to that 73-degree house that I like. And that's our basic refrigeration cycle.